Good morning, students. Today we will discuss about acid base balance. Under the acid base balance, we will discuss what is acid, what is base, what is pH and buffers. Coming to the what is acid, molecule that donates the protons or H plus ions, that is called acid. It's sour to taste and it turns blue litmus paper to red color. And examples of acids are HCl. It dissociates into H plus and chloride ions, and carbonic acid, it dissociates into H plus and bicarbonate ions. These are the examples of acids. Next, coming to the base, molecule that accepts protons or H plus ions, it bitter to taste and it turns red litmus paper turns to blue. Examples are carbonic acid and hydrogen dihydrogen phosphates. Carbonic acid plus H plus ions to bicarbonate plus H plus ions to form carbonic acid, and hydrogen phosphate plus H plus ions to form dihydrogen phosphates. This is the acid and base. Next, coming to the metabolic sources of acids and bases. First one is metabolic sources of acids. During metabolic process, two types of acids are produced. One is fixed acids or non-gaseous acids. Phosphoric acid and sulfuric acid produced from metabolism of dietary phosphoproteins and lipoproteins. Organic acids are pyruvic acid, lactic acid, acetoacetic acid, beta hydroxy, butyric acid and uric acid. Next, coming to volatile acids. Volatile acid is carbonic acid. In physiology, carbonic acid is described as volatile acid or respiratory acid. This carbonic acid is respiratory acid because it's only acid excreted as gas by the lungs. It plays important role in bicarbonate buffer system to maintain the acid-base homeostasis. Next, metabolic sources of bases. Catabolism of few food materials produces bases. For example, citrate salts of fruit juices may produce bicarbonate salt, and deamination of amino acids produces ammonia. Then formation of biphosphate and acetate also contributes to alkalizing effect. Next, coming to the fate of hydrogen ions. In aerobic process, gluconeogenesis uses hydrogen ions. Citric acid ingested as their sodium, potassium salts are metabolized to carbon dioxide and water. Fruits are major source of alkali in the diet. Next, these are the pH, acids, bases, strong acids, weak base acids and pK value, alkali reserve buffers. What is pH? pH is negative logarithm of hydrogen ion concentration. Normal blood pH is 7.4, range is 7.38 to 7.42. Acids means it donates the protons and pH is less than 7. Bases are accept the protons, pH is greater than 7. What is strong acids means acids which ionize completely, that is called strong acids. For example, HCl. Then weak acids means which ionize incompletely. So example is carbonic acid, then pK value, alkali reserve and buffers. See, pH in numerical scale that measures acidity and alkalinity is called as the pH scale. It turns from 0 to 14, 0 to 14 with neutrality is, this is the neutrality, pH is 7. It indicates the concentration of free H plus ions in water. Solution is considered neutral when the number of H plus ions equals the number of hydroxy ions. This solution is neutral at pH is 7. This is the pH scale, and this is the less than 7 is acid and greater than 7 is base. Neutral pH is 7. Next, coming to the blood pH of plasma is 7.4. In normal life, the variations of pH is very small. The pH of plasma is maintained within narrow range of 7.38 to 7.42. What is acidosis means? If pH is below 7.38, it's called as acidosis. Life is danger when pH is decreased below 7.25. This acidosis leads to CNS, depression and coma. Death occurs when pH is below 7.0. Next, alkalosis. When pH is more than 7.42, it's called as alkalosis. It is very dangerous if pH is increased 7.55. Alkalosis induces neuromuscular hyperexcitability and tetany. Death occurs when pH is above 7.6. This is the acidosis and alkalosis. Next, coming to this is the pH of some common items, and 1 molar NaOH pH is 14, and ammonia pH is 12, blood pH is 7.42, then pure water 7, milk is 6.5, and lemon juice 2.5, stomach acids are 2, and 1 molar HCl is 0 pH. Next, pH of biological fluids. Serum and CSF pH is 7.35 to 7.45. Pancreatic juice 7.5 to 8. Saliva 6.35 to 6.85. Arterial blood is 7.38 to 7.42. Venous blood 7.3 to 7.38. Urine pH is 4.4 to 8.0. Gastric juice 0.9 to 1.5. These are the different types of pHs in different analytes. Next, coming to the what is pKa. The pH at which the acid is off ionized is called as pK of an acid. This is constant at particular temperature and pressure. Strong acids have low pKa and weak acids will have higher pKa. This is pKa. pKa means pH with acids is awfully ionized is called as pKa of an acid. Next, coming to the Henderson-Hasselbalch equation. This equation is relationship between pH, pKa, concentration of acid and conjugate base. It is expressed by Henderson-Hasselbalch equation. This is the equation. pH is equal to pKa plus log salt by acid, log base by acid, and base is the numerator and acid is the denominator. When the concentration of base and acid are the same, the pH is equal to the pKa. This is the equations. For example, carbonic acid. Carbonic acid dissociates into H plus and plus bicarbonate, and this law of mass action at equilibrium, Ka is equal to H plus bicarbonate by carbonic acid. This Ka is dissociation constant of bicarbonate. This equation may be rewritten as H plus is equal to Ka and H2CO3 carbonic acid by bicarbonate. We know the pH is equal to log 1 plus 1 by H plus. See, by taking the reciprocal by logarithms, log 1 by H plus equal to log 1 by Ka plus log acid by base. Then log 1 by Ka is equal to pKa. This equation 3 may rewritten as pH is equal to pKa plus log bicarbonate by carbonic acid. The above equation is valid for any buffer systems. The general equation is referred to as Henderson-Hasselbalch equation. For any buffer is written as pH is equal to pKa plus log base by acid. Applications of Henderson-Hasselbalch equation. This Henderson-Hasselbalch equation is used to calculate the pH of solution, and it shows increase in the concentration of salts or bases is responsible for increase or decrease in pH. It is the importance of alternating the ratio of salt is to acid in the concentration of regulating the pH. These are the uses of Henderson-Hasselbalch equation. Next, coming to the mechanism of action of regulation of pH. There are three types. One is buffer system. Buffer system is the first line defense. Respiratory mechanism, second line defense, and renal mechanism is third line defense. First, coming to the first line defense, buffer system. First, what is buffer? Buffer is defined as solution of weak acid and its corresponding salt which can resist a change in pH it caused by the addition of acid or base. The pH is the negative logarithm of hydrocyanide concentration. Then blood pH is 7.4. Buffers are mainly two types. One is mixture of weak acid with their salt and strong base, and mixture of weak base with strong acid. These are the different types of buffers in plasma and erythrocytes. Buffer of extracellular fluid present in plasma, bicarbonate buffer, phosphate buffer, and protein buffer, and buffers of intracellular fluid present in red blood cells, bicarbonate buffer, phosphate buffers, hemoglobin buffers. Then urinary buffers are disodium hydrogen phosphate and sodium dihydrogen phosphates. These are the urinary buffers. Urinary buffers are examples of phosphate buffers. Next, coming to the bicarbonate buffer system. Examples of bicarbonate buffer systems are bicarbonate or carbonic acid. The most important buffer is ECF is bicarbonate buffer. This bicarbonate buffer is present as sodium bicarbonate in the extracellular fluid and potassium bicarbonate in the intracellular fluid. Here this carbon dioxide plus water to form carbonic acid by the enzyme carbonic anhydrase. This carbonic acid dissociates into H plus bicarbonate. Carbonic acid is formed when carbon dioxide reacts with water. This reaction is catalyzed by the enzyme carbonic anhydrase. Carbonic acid dissociates spontaneously to form proton and bicarbonate ion. Then pK of carbonic acid is 6.1. Some normal values are normal pH is 7.4. Then pK of bicarbonate buffer is 6.1 and bicarbonate concentration is 24 millimoles per liter. Then partial pressure of carbon dioxide is 40 mm per Hg. Then constant of carbon dioxide is 0.03. So carbonic acid is equal to 0.03 into partial carbon dioxide and 0.03 into 40, 1.2 millimoles per liter. The carbonic acid concentration is proportional to the partial pressure of carbon dioxide. The Henderson-Hasselbalch equation for bicarbonate buffer. Then pH is equals to pKa plus log bicarbonate by carbonic acid. Then substituting the values, the pH is equal to pKa, bicarbonate pKa is 6.1 plus log bicarbonate is 24 and carbonic acid is 1.2. Then 6.1 plus log 20, 6.1 plus 1.3 equal to 7.4. Then pH is equal to bicarbonate buffer. The pK is 6.1, so it should not be effective buffer at pH 7.4. But still it is the most important buffer because it's high concentration and the two elements of the buffer system are regulated by two different systems. Base component of bicarbonate is regulated by kidneys. Acid component is regulated by respiratory system. Under physiological conditions, the ratio of bicarbonate to carbonic acid is 20:1. This represents the alkali reserve of the body. This ratio is called as buffer ratio. So this is the bicarbonate buffer system. Next, coming to the phosphate buffer system. The most important cellular fluid and tubular fluid, renal tubular fluids. And then pK of phosphate buffer is 6.8. This is the close to physiological pH. The ratio of phosphate buffer is 4:1 at physiological pH. Then the buffering capacity is less than bicarbonate buffer because its concentration in extracellular fluid is low. The important in renal tubular fluid as low pH than plasma. Phosphate is usually concentrated in the tubules and this is the phosphate buffer system. Next, coming to the protein buffer system. In the blood, proteins, especially albumin, acts as buffer because This protein containing large number of carboxyl and amino groups in their structure. The protein acts as base and ammonia group takes up hydrogen ions and forming ammonia. Then proteins acts as acid. The acidic carboxylic groups gives hydrogen ions forming OH groups of alkali to water. The side chains has especially imidazole group of histidine. Buffering capacity depends on the pK value of ionizable side chains. This ionizable group pK is 6.7. Albumin has 16 residues of histidine. Next, coming to the hemoglobin buffer system, then hemoglobin acts as buffering agent. This buffering is due to imidazole nitrogen group which remains dissociated in acidic media and base forms. Oxygenated hemoglobin is stronger acid than deoxygenated hemoglobin. This imidazole nitrogen group acts as the acid and donates the protons. Deoxygenated hemoglobin is less acidic, less dissociable, and imidazole group acts as the base and takes up the hydrogen ions and form the medium. The acidity of the medium favors the delivery of oxygen and alkalinity of the medium, it favors the oxygenation of hemoglobin. This is the hemoglobin buffer system. Next, coming to the respiratory mechanism. In the lungs, this is the second line defense. In the lungs, the formation of oxyhemoglobin from deoxygenated hemoglobin releases hydrogen ions. This reacts with bicarbonate to form carbonic acid. Low carbon dioxide in the lungs, the equilibrium shifts towards production of carbon dioxide and eliminates the carbon dioxide through air. In the tissues, at the tissue level, hemoglobin binds to hydrogen ions and it helps to transport carbon dioxide as bicarbonate with minimize the pH. This is called as isohydrate transport. You can observe here. See, in the RBC, plasma carbon dioxide enters into the erythrocytes. This carbon dioxide combines with water to form carbonic acid by the enzyme carbonic anhydrase. This carbonic acid dissociates into H plus and bicarbonate. This H plus ions trapped by hemoglobin, and this carbonic acid concentration is more in erythrocytes, and this enters into the plasma exchanger of chloride ions to maintain the electrical neutrality. Next, respiratory regulation. Lungs excrete or retain carbon dioxide. It depends on the blood pH. When blood pH is low, it causes respiratory center is stimulated, then hyperventilation. It leads to lungs rapidly excrete the carbon dioxide and it decreases the partial carbon dioxide. It leads to pH is increases towards the normal, and this is the increase the pH. When blood pH is high, respiratory center is inhibited. It leads to hypoventilation and carbon dioxide is retains in the lungs and it increases the partial carbon dioxide and it leads to decrease the pH towards the normal. This is the lungs excrete or retain carbon dioxide depends on the blood. Next, coming to the renal regulation of blood pH. This is the third line defense in acid-base balance. By excreting the H plus ions and stimulate the reabsorption of bicarbonate, the four major mechanisms are there. One is excretion of H plus ions and generation of bicarbonate, reabsorption of bicarbonate, excretion of titratable acid, excretion of ammonium ions. First one is excretion of hydrogen ions and generation of bicarbonate. It mainly occurs in proximal convoluted tubule. Carbon dioxide is combined with water to form carbonic acid by the enzyme is carbonic anhydrase. This carbonic acid then ionizes to give H plus ions and bicarbonate. These H plus ions are exchanged for sodium, which are reabsorbed along with bicarbonate into the blood. You can observe here this H plus ions, this occurs in proximal convoluted tubule, and here carbon dioxide is combined with water to form carbonic acid by the enzyme is carbonic anhydrase. This carbonic acid ionizes to give H plus ions and bicarbonate. This H plus ions enters into the tubular lumen, and this bicarbonate enters into the plasma by the exchanger of sodium ions. Next, coming to the reabsorption of bicarbonate. Bicarbonate is present in the proximal convoluted tubule. This bicarbonate combines with H plus ions to form carbonic acid by the enzyme is carbonic anhydrase. On the brush border, this carbonic acid dissociates into water and carbon dioxide, and this carbon dioxide diffuses into the cells and combines with water to give H plus and bicarbonate. These H plus ions are exchanged for sodium, which is reabsorbed along with bicarbonate into the blood. There is no net excretion of H plus ions or generation of bicarbonate. See here, water and carbon dioxide combines with to form carbonic acid by the enzyme carbonic anhydrase. This carbonic acid dissociates to form H plus and bicarbonate. This H plus ions enters into the tubular lumen, and again it combines with bicarbonate to form carbonic acid. This carbonic acid again converts to carbon dioxide plus water by the enzyme is carbonic anhydrase. This carbonic acid bicarbonate enters into the blood by the exchanger of sodium ions. Next, coming to the excretion of titratable acid. Titratable acidity is measure of acid excreted into urine by the kidneys. The major titratable acid is present in urine is sodium acid phosphatase. Due to sodium and hydrogen ion exchange, the sodium disodium hydrogen phosphate is basic phosphate. It converts to acidic phosphate. That means sodium dihydrogen phosphate, which is excreted in urine. The excretion of titratable acid enables constant excretion and elimination of acid from the body. You can see here in the tubular lumen, Disodium hydrogen phosphate is dissociates to form sodium plus sodium hydrogen phosphate. And here in the tubular cells, water combines with carbon dioxide to form carbonic acid. This carbonic acid dissociates into H plus ions and bicarbonate. These H plus ions are excreted in tubular lumen and it again combines with sodium hydrogen phosphate to form sodium dihydrogen phosphate. This sodium dihydrogen phosphate excreted in urine. As the tubular fluid it moves down the renal tubulus, more and more H plus ions are added. It results in the acidification of urine. So this causes decrease in the pH of urine as low as pH is 5.4. This is the excretion of titratable acid. Next, coming to the excretion of ammonium ions. It occurs with digital convertible tubule. Excreted ammonia traps H plus ions in the urine to become ammonium. This ammonia is combines with H plus ions to form ammonium. In glutaminase is the tubular cells hydrolyzes the glutamine to ammonia and glutamic acid. This ammonia is diffuses into the lumen and it combines with the hydrogen ions to form ammonium. This ammonium can't diffuse it back into the cells, therefore excreted in urine. You can see here this glutamine is converts to glutamic acid by the enzyme is glutaminase, and here ammonia is enters into the tubular lumen. This ammonia combines with H plus ions to form ammonium. This ammonium is enters into the cells, so it excreted in the urine. This ammonium is the major urine acid.